Good morning, students. In today's class, we are going to study about the Heisenberg's uncertainty principle followed by the complementary principle. Okay, so complementary principle, I will take it at the last after explaining this uncertainty principle. Okay, in the previous lectures and in the previous videos, we have studied about the de Broglie's concept of matter waves and how the path of how electrons were chosen for the experimental studies by Davison and Germer to prove that the electrons have a particle nature before it hits the target material of nickel, and after that a diffracted beam of waves of diffracted beam of electrons are coming out of the nickel crystal after diffraction. So after the hitting of the target, there is a wave pattern that is followed by the electrons as a diffracted beam in a wave pattern. So Davison and Germer experiment proved that the electrons can behave as a particle as well as it can behave as a wave. Okay, so both the dual nature of it can be explained in a single experiment. Okay, so in those time, in this 19th, lots of studies were going on with the duality, okay, to prove and to disprove. Okay, so Heisenberg also came up with a certain concept because electrons were the basic one which was chosen as a particle, and its wave nature were also studied, isn't it? So Heisenberg, in the experimental studies of Davison and Germer and in other experiments, consecutive experiments, he was trying to say that it is difficult to measure the position and the velocity simultaneously. It is difficult to determine the position of a particle or the momentum of the particle at the same time. If you are trying to find the position accurately, you will not be able to measure the momentum of the particle accurately. Both cannot be measured simultaneously accurately. Okay, I repeat. Okay, Heisenberg's uncertainty principle says that it is not possible, or I can say it is difficult, okay, to determine okay, to determine the position of the particle. Say, example, an electron is moving in this circular orbit. Okay, so the electron is moving in the circular orbit in this direction. Okay, if you are trying to find this position of this electron, okay, you can try with certain experimental method. Like here, I will explain you. Okay, before that we will finish this. It is difficult to determine the position and the momentum. Okay, momentum of a particle. It is difficult to determine the position and the momentum of a particle accurately at the same time. Means simultaneously, I can write. Okay, simultaneously. Hope you are able to see this one. Okay, so it is said that it is difficult, okay, to determine the position of the particle and the momentum when the object is in motion. Okay, both, or I can say momentum has mass into velocity. Okay, mass of the particle is the same, mass of the electron is the same, so that is not unchanged, but the velocity mv, because momentum p is equal to m into v, right? So the velocity of the particle, I can say, okay, both cannot be measured, both the velocity of the particle and the position where the electron is there at a particular time, both to measure at the same time is difficult, or I can say you can find it, but there will be an error associated with it. Okay, you cannot say that I have 100% can find the position of this electron when it is moving with some velocity. Okay, so that was a concept that was explained by Heisenberg. So the word uncertainty comes. Okay, you can say approximately I can find that this may be the position of the particle, and approximately you can say that this may be the velocity of the particle, but that will be associated with an error factor. Okay, that is what Heisenberg was saying. This was introduced after this de Broglie concept of the dual nature concept, okay, by the de Broglie. Okay, so for example, let's come to this picture. Okay, imagine that there is an electron moving in this path. Okay, to find the position of the electron, what to do? Unless and until we allow a photon to hit on it. Okay, it's a very microscopic particle. Okay, so like in the Compton effect, you have studied, isn't it? That a photon, a single photon is allowed to fall on an electron and they collide with each other. And then the photon will be scattered on one place and the electron will be scattered, recoiled in the another direction with a kinetic energy with some angle. Okay, the same similar concept we are going to take in order to find the path. Actually, we are interested here to find the position of the electron, because already the electron is moving. The electron is in the motion. Okay, is in moving in the, imagine that it is moving in an orbit or in a particular path. Okay, so when the electron is moving, okay, it's difficult to find the position of the electron. So there was an experiment that is done, okay, by allowing the photon to fall on it. Okay, when a lighter photon is allowed to fall on it, what will happen is there will be a collision that may take, okay, the electron will be hit and the photon will be scattered here. Okay, the photon will be scattered, like in the case of the photoelectric effect. Okay, a photoelectrons will be ejected, and after hitting this electron, it will be the path of the photon will be retraced and it will go up, and this can be viewed in a microscope. Okay, so there you can find out that this is the path of the electron. When an photon hits and goes and it is able to be seen in the microscope, then you will know that that will be the position of the electron. In those days, to find the electron position is not so easy. Okay, so they tried this experiment to find out the position when the photon hits and then retraces its path, and if it can be viewed within the microscopic setup in this region. So whenever you get a photon, a photoelectron like a thing in the view of the microscope, then you will know that will be the position of the electron. Okay, so the position of the electron could be found out using this experiment, and at the same time, after hitting, the electron can take a new path. It may not go into this path, isn't it? Earlier it was moving in the circular orbit like this. Now, do you say that the electron will only move in the circular orbit like this? No, because there is a collision that has happened here. Okay, so there is a chances that the electron can take a new path and the velocity also will change, isn't it? Obviously, because during collision it can lose some energy and it can there is a chances that it can go in a different path compared to the path of the circular orbit that was expected. Okay, so when I try to find the position, okay, the electron which was already moving with some momentum, okay, momentum includes mass into velocity. Mass of the electron will remain constant throughout, but the velocity will change, isn't it? So the velocity of the electron, okay, will definitely be not the same as it was moving in this position before this point. Okay, so it was said that when I try to locate the position, when I concentrate my experiment, in order to find the position of the experiment, I keep concentrating on one concept of finding the position. Yes, I can find it accurately, but at the same time, the velocity part, I will not be able to measure accurately. That means I can measure, but with an inaccurate way or with a error factor. Okay, there may be some error associated with it. Okay, both to measure simultaneously and both to measure accurately is not at all possible. There may be error with one factor or the other when you're trying to measure. That concept was explained as an uncertainty principle by German scientist called Werner Heisenberg. His name is W-E-R-N-G-E-R, Werner Heisenberg, but we always call it as Heisenberg's uncertainty principle. Okay, I hope it is clear to you. Okay, so the equation, he said that the position, okay, the position can be expressed as delta x. Okay, I'm going to write it in the equation form. Okay, the position of the electron here, it can be electron, it can be any other one also. Okay, but for convenience sake, electron was chosen. Okay, so let the position, okay, the position of the electron determination, the position determination, okay, is taken as delta x, okay, and the momentum determination, okay, let this be the position and the momentum be delta p. Okay, if we take delta x and delta p, okay, shall I rub this? Hope this is clear. So shall I rub this one? So if delta x is the position of the particle, okay, if delta p is the momentum, is a momentum of the particle, then according to Heisenberg's concept, okay, delta x by delta p is equal to Planck's constant divided by 4 pi. Okay, the product of delta x into delta p, okay, is equal to h by 4 pi. Okay, again, delta p can be written, momentum part can be written as delta x into, okay, since the momentum p is equal to m into v, na? Okay, so I will write this m into v, but I have to say that velocity cannot be determined accurately. Okay, mass of the electron remains the same value, but velocity before the photon hits, the velocity may be uniform. Okay, do you remember this figure? Here, the path the electron was moving, the velocity may be equal, but after this, okay, the velocity may not be same. So I cannot put this one as v, but I have to put it as delta v. Okay, delta v, okay, you understand this, will be equal to h by 4 pi. Okay. So I have to say that, okay, I can also write this equation as delta x into delta v is equal to h by, okay, m into 4 pi. Okay. This is also another way of writing the Heisenberg's principle. This is a very important question. Usually this will be asked sometimes in 2 marks or in a big derivation. The proof of this Heisenberg's uncertainty principle is also there by using a gamma ray experiment, okay, which we will study it in the next class, okay. So for time being, now I have explained in today's class about the Heisenberg's uncertainty principle of the determination, saying that it is difficult to find the position and the momentum of a particle accurately. It can be measured provided that one may be accurate, one may not be accurate, or both with the error factors, we will be able to find the simultaneous determination of the position and the momentum and the product of delta x. Here I'm not using x and p, I'm using delta x and delta p. Delta x and delta p refers to the error. There is an error that is associated with the determination of the position of the electron or the momentum of the electron, and momentum we have written it with respect to the velocity. Okay, so ultimately it is a error associated with the velocity into the delta x position will be equal to h by m into 4 pi. Okay, so you can write it this as a main concept, and this also can be written as this way. Okay, so hope this one is clear about the uncertainty principle. Now, based on the same concept, okay, we are going to also study what is called as a complementary principle. Okay, the experimental fact we will explain and study it in the next class. Now, I will move on to what is called as the complementary principle. Okay. Based on the same concept of the uncertainty principle, okay, about the position and the momentum determination, we also studied in de Broglie's concept that the wave is a particle can exhibit as a particle, okay, that we have studied in the matter wave. No? Let's come back to the matter wave explained by de Broglie. Okay, it is called as a de Broglie wave also, that the particles, okay, there are particles embedded in the wave and they are moving, okay, and the distance between, okay, one crest to crest, one node to node, antinode to antinode, we call it as a wavelength, isn't it? So matter waves include both the particle and the wave. Okay. Based on the de Broglie concept came another concept called as complementary principle explained by Niels Bohr. Okay. Niels Bohr was contradicting this concept of the matter wave, and he was saying that he said that there is an inability to observe the wave particle aspect of the matter wave at the same time. Okay, the complementary principle goes like this: the inability to observe the wave and the particle aspects. And the particle aspect of matter at the same time. At the same time, okay, is known as the complementary principle. Okay, like how in Heisenberg principle we are studying that it is difficult to find the position and the momentum simultaneously. The same way, Niels Bohr brought a concept saying that it is difficult to observe the wave and the particle, okay, aspect of a particular matter simultaneously at the same time. It is difficult to observe a particle as a wave or as a particle as a particle itself. Okay, that was a concept introduced by Niels Bohr. That means what he tried to explain is, he said that at the same time, it is difficult to understand the wave as a particle or the particle moving as a wave. Okay, so the dual concept explained by de Broglie was contradicted by Niels Bohr, but he said that it can be, because in quantum mechanics, we need to take it. We need to accept that fact that particles are moving. The electron, the example I'm taking, the electrons are moving as a particle and the electrons are also moving as a wave. Okay, but he said that it is difficult to observe them simultaneously. The simultaneous concept is very important. At the same time means simultaneously. At a particular point of this one, you cannot say that a particle, that a wave, if the wave is having a, if the particle is moving like a wave, it is difficult to accept it to move as a particle at the same time. One phenomena can be accepted and understood, but both together at the same time to take it up, okay, as the electron moving as a particle, as the electron moving as a wave, is at the same time to understand is difficult. Suppose the electron is behaving like a particle, I can say at a particular time. In that case, the wave nature of the electron will be less. Okay. If I consider, I repeat, if I consider that electron is moving, okay, as a particle in the Davison German experiment we studied, the electron was initially moving as a particle form. Okay. If you take that electron is moving as a particle, that means at that particular time, the wave nature of the electron cannot be taken into account. And if after the collision in the Davison experiment, I said that there is a diffracted beam giving interference and showing the diffraction pattern like a wave is coming out, in that case, only the wave nature of the electron exists, and I cannot accept or I cannot say that the particle nature is existed by that particular wave. So both together, it is not possible to say that the electron behave as a particle as well as the electron behave as a wave at the same time. Okay, similar to the Heisenberg principle itself, this is also another principle which I was saying, if there is a particle nature, that means wave nature is minimum. If a particular electron is behaving like a particle, that means the particle nature is around 80%, I can and say that the wave nature can be around 20%. If I say that the particular electron is behaving like a wave, that means the wave can be 80 to 60% nature, and in that case the remaining percentage will be the particle nature. I cannot say that a particle and the wave nature exist together at the same time at a particular point of time, and 100% it is a particle and a wave existing together. So Niels contradicted and explained this. Okay, his contradiction was against the de Broglie concept of the wave and the particle nature existing together as a matter wave. Okay, so he contradicted and said it's difficult to understand a particle to exist in both as a particle as well as a wave pattern simultaneously. Either one will be high. If I say the particle nature is exhibited by the particular electron in that particular experiment, I can say that it is high. That means the electron is now behaving as a particle. That means the wave nature is zero or suppressed or minimum. Or in some other case, I can say the wave nature is higher. In that, the meaning is that the particle nature is suppressed or minimum. Either one can be high and one can be low when you try to determine. And I cannot say that both exist together and both are 100% equally existing at the same particular time. So this principle is called as the complementary principle as explained by Neil Bohr. Okay, I hope you are clear and hope you are able to understand this two concepts. And this question is somewhat important in the examination point of view. It can be asked in 2 marks. Okay, so the inability to observe the wave and the particle aspect of a matter at the same time is called as the complementary principle explained by Bohr. Okay, so I hope it's clear and thank you for watching this video. Now I will end this video here for today's class. Thank you.